Oh hey, we are live. The internet can totally see me now. Alright, let's see. Stream health is excellent. Alright, hello everyone. Welcome to the meshoptimizer stream, where I'll talk about what I'm gonna do in a bit. Let me double check the sound quality. I'm hoping that it's gonna be fine now, but I want to make sure. Alright, I like the sound quality. So yeah, after the issues on the last stream with sound, and also I watched the stream, I guess, before that did not have the dual mic problem, and it also didn't have the sound that was super awesome. So I kind of kept in, and I bought a Blue Yeti mic, and it's kind of expensive, but I like the sound quality. So we will assume that it's all good, and we'll start the stream. Let me know if there's any issues with the audio on your end or whatever else. So we will be talking about, we will be trying to build a prototype of a technique that I wanted to try for a while. I have this to-do list where I gather a bunch of stuff that I want to do for the different open source projects that I work on. And there was this entry in the to-do list for a while, which I wanted to get to. And so I researched the topic a bit last night, and I'm kind of less excited about this algorithm than I used to be. But we'll still try to implement this. I'm hoping that we can get this running, and then we will see how it works, or maybe we won't get it running, but whatever happens, happens. This is a class of, wait, hold on, come on. Wait, what's happening with my Linux thing? That's not Linux. Oh, okay, good. What? So yeah, this is a class of prototypes that might not ship or might ship. I'm occasionally doing work on meshoptimizer that's experimental, and I have no idea what will actually happen with this. And then I either sort of finish it and then I commit it. Oh, by the way, this was the stream work that we've done, which I have submitted, so that's good. Yeah, and some of this is, I guess, failed experiments. I did some compression work some time ago, which didn't really work out. This might get in at some point, but yeah. So point being, we'll be writing some code. This code might not be the final shape of the code that is submitted. This code might never be submitted, but we'll try to make something work and see how that performs. So what are we doing today? So the traditional, or the popular way how LOD systems work, and let me see if that's well, that's fine. Let me actually, let me just switch to different mesh. And let's try this. All right. Oh. Did I break the rotation code? Interesting. All right, whatever. This is kind of odd, but I will not debug this right now. So, so the canonical way how mesh LOD systems work in many games is discrete LODs. So you start with a mesh that is kind of fine-grained, and then you say, hey, like here's the next level of detail that has fewer triangles. Here's the next one. Here's the next one. Here's the next one. 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 And so in this case, the sequencing and the final one. The sequencing is kind of not too aggressive because it goes like 1.5x for every LOD, which means that you can switch the level of details, levels of detail discretely. So at some distance, you just switch to different mesh, and you hope that the difference is not too apparent, which it might be or might not be, right? So like in this case, the hope is that at some distance, the difference between these two LODs isn't that that apparent, right? And the difference between these is even less apparent. So this is all fine and good. This makes for a really simple implementation at runtime, but this is not necessarily what you want. So there has been this desire to do progressive LODs. And what progressive LODs mean is that you take a mesh that's like some number of triangles. Let's just assume that this is like a grid, right? And then you say, okay, I want to remove like 2 triangles from this mesh, just 2. So then you say, okay, let me, instead of this, we will make a mesh that still preserves the tessellation in the in this part, but just has 2 triangles in the upper right corner. And then you say, okay, I want to remove like 2 more triangles or like 3 more triangles or whatever. And then you progressively, maybe takes you, in this case, it takes you like 10 steps to get to the super basic mesh that just has 2 triangles, right? And so the idea is that as the mesh goes farther and farther away from camera, you do these small modifications to the mesh where you just remove 1 or 2 triangles at a time, or like 2, 3, 4, like a small number, right? And then it is really hard to see the difference because the human eye is really good at catching like large abrupt changes, but it might not be very good in catching, it's like slightly worse at catching like small changes, right? And even if the result is the same, going directly to this 2 triangle mesh might be more jarring, even if the transition happens kind of at the same distance where it would happen otherwise. The problem is that when you're trying to render a lot of different meshes, it is hard to remove like a few triangles from a mesh at a time because it requires modifying mesh data in memory. What happens if you have like 100 or 1,000 copies of this quad in your scene, in your view frustum, and then they are all at different distances? Do you have to maintain like 1,000 copies of this mesh separately in memory so that you can like patch each mesh separately and remove a few triangles from each mesh? So that doesn't really scale, which is why a lot of games just do discrete LODs where you pre-compute like 4 to 8 to 10, maybe 10 is like kind of extreme, I guess, but yeah, like 4 to 8 levels of detail, and then you just switch between them, which is kind of what I think is a reasonable idea, and this is what my algorithm is designed for. But there is this cool idea of a sliding window. So the idea, I'm not sure where the idea is coming from, but I guess it was popularized, at least. I'm not sure who invented this, by Tom Forsyth. He wrote an article in what was it? Game Programming Gemstone. This is from like a while ago. I don't know, 2000. It's an old book. Let's see. 2001, right? So, but you know, like the book, you can buy the book. The book is on Google Books, but half of the pages aren't there. There is copy of this article on Tom Forsyth's website. Unfortunately, this copy didn't quite survive the transition from what I would guess was Microsoft Word to web. I think these are like various quotation marks and apostrophes and whatnot, so it's not super easy to read. Yeah, okay. But whatever, it doesn't have pictures, but at least this has full information and gives you a general idea. But I will describe the actual process right now. So here's the idea. As we talked before many times, the core of the mesh optimizer algorithm, as it stands right now, is edge collapses. So we take a mesh, and then we say there's two vertices that are connected with an edge, and then there's some triangles around these guys. And then we want to remove this edge from the mesh, and we want to remove this in this direction, which means that the the orange vertex moves to the green vertex. The orange vertex disappears from the mesh, and then all triangles, so some of these triangles, the triangles that belong to this edge, like these ones, these are just dead, like they're gone from the mesh. And then these other triangles, the blue ones, these ones, they're still in the mesh, but they change because the vertex that was the orange vertex is now the green vertex, right? So let's number these triangles, and let's assume that this is our mesh. So there's not like this. This is just however many. What was it, like 3, 5, 6, 7, 9, 10 triangles. So this is our mesh, right? And let's look at what the sliding window technique says you can do. All right. So I will number this triangle. So this was like 1, 2. All right, whatever, it's visible, sort of. 3, 4, 5, 6, 7, 8, 9. So we had 9 triangles in the original mesh. After the modification, here's what happens. So let me draw the same skeleton structure. I guess I could copy this one, but whatever. All right. Now we are removing. Oh, this will not end well. All right, we are removing this vertex. Damn it. All right. Okay, let me do this. Let me hope that this works better. All right, so we leave 6, 7, 8, and 9 as is. They do not change. 2 and 5 are gone. Now, so this vertex is gone. And we have this edge. This edge and this edge. So the triangles 2 and 5 are removed, and the triangles 1, 3, and 4, they change, right? They become larger. So what the sliding window technique says is that you could think of your mesh as a long series of triangles that are split into 3 parts. So there is the middle part, which has all of the triangles that were not modified. In this case, it's 6, 7, 8, and 9. So let's 6, 7, 8, and 9, right? Now there is the part before the early part of the mesh, where there is all of the triangles that were either modified or removed. So in this case, it's 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. And then on the right hand side, after the triangles that were not modified, we will have the triangles that were modified, not the ones that were deleted, but that were modified, but they are now different, right? So let's call them actually 1 prime, 3 prime, and 4 prime, because they are technically different, right? One of the vertex is now different, vertex is now different. And then the technique says, hey, put this triangle here, this triangle here, this triangle here. And then the technique says, okay, given a list of triangles like this, if you were to draw the prefix of this would be your original mesh. If you were to draw a suffix, which is this one, then it would draw the new mesh after the simplification. If you wanted to do other simplifications, like if you wanted to remove another edge, you cannot modify the triangles 1 prime, 3 prime, and 4 prime, because the technique doesn't really work like this. But what you could do is you could modify some of the ones in the previous section. Let's see. So for example, there could be a second collapse that takes this edge and removes it. Well, that's kind of bad collapse. But okay, fine, whatever. Let's say the algorithm decided to remove this edge, and you can collapse an edge in either direction. In this case, though, if you collapse the edge like in this direction, all right, my drawing skills today suffer from, I don't know what they suffer from. So if you try to collapse the edge in this direction, you would be modifying triangles 1 prime, 3 prime, and 4 prime again, which we cannot do. But you can collapse the edge in the reverse direction, and so like this one. Which is gonna be fun. So in this case, triangles 6 and 7 go away. The rest of the mesh stays as is, right? I will not draw this, but it's kind of obvious what happens. So in this case, the technique says, fine, you can have another sort of layer, which is if you started to render the mesh from the triangle 8 up to the end, it's still a valid mesh that is the result of the simplification. So in this case, we kind of cut off a corner, but if we actually had extra triangles here, like this, then it would be less problematic and it would have worked fine, right? And so if you order the triangles in this buffer appropriately, and you have this redundancy where the triangle 1 now has a copy of 1 prime, and if you never modify 1 prime again, so like any triangle that has been modified at least once should stay as is, then the technique can work. And so in this case, we have one buffer that has, let's count these guys. It's kind of, let's just ignore this third thing for now, and let's just say we were doing two, like one collapse, right? So we have one buffer that has 12 triangles. And we can pick a range of this buffer that means either the mesh before the modification or the mesh after the modification. If we were doing this using discrete LODs, where each LOD is just one set of triangles, then we'd have to have 1 through 9 as the first LOD, which is like 9 triangles, and 6, 7, 8, 9, 1 prime, 3 prime, 4 prime, which is 7 triangles, as the second LOD. So we would have to use 16 triangles, like enough memory to represent 16 triangles, right? To represent these two levels of details. And the sliding window technique says we only need 12. And the theory is that if you're doing more than one collapse, then you can just do them one at a time in this relatively large buffer up to a certain point. The point is, since you can't modify triangles 1 prime, 3 prime, and 4 prime again, the more triangles you modify, kind of the more restricted your simplification process becomes. Which means that at some point you just stop and you say, I can't change any triangles that I have already changed. There are some triangles that I could change, but I really don't want to because they are a really bad collapse. Like in this mesh before, where I said you can collapse the edge between 6 and 7 in the sort of reverse direction. It's like a really bad collapse. It really deforms the mesh. And so you say, okay, fine, I'm done. And then you can say the LOD levels after this need a separate sequence of indices. And this is what we are trying to do today. And I don't know if we'll succeed because it's a relatively involved process. And, you know, who knows if it works. So let me just start doing this. I will, in the interest of trying to get something done, I will try to not stop too much and like talk about stuff that I'm doing and just do stuff. But I don't know how well that will work out. So, the way my algorithm works right now is that it goes through triangles, then it gathers as many collapses as it possibly can do. It sorts them by the collapse error, and then it does some heuristic on like what we can do, and then it does as many collapses as it can do in parallel. In parallel doesn't mean that it's doing it on multiple threads, although it could sort of do this, maybe, kind of. In parallel means that it does the collapses without, how do I put this? Like after one edge is collapsed, basically, the algorithm says, I don't want to touch any of these two vertices again. Which is kind of similar to what this technique wants us to do. This technique wants us to say, once we collapse an edge, we don't want to touch any vertices in any triangles that were in this original vertex. And so the first thing that we'll do is we'll kind of modify our algorithm to do that and just see sort of what the result of this is in terms of how many things we can collapse. So I wanted to pick a smaller mesh for this because I'm worried that like it will not be fun otherwise. So that's a reasonably small mesh. I kind of wanna, oh no, that's a bad mesh. It has facets. Facets are bad for my algorithm right now. Damn it. Alright, let's see what else we have. I guess I want, how do I sort by size? Oh, alright. Aha, dashes. No, dash, oh, dash, okay, cool. So, alright. I'm trying to pick a mesh that's kind of small enough so that the restrictions of this algorithm aren't penalizing us too much, but large enough that we can actually simplify it to some meaningful degree. Where's this Arctic Fox guy or gal? Let's see. This might be fine. Let's see. I have a lot of meshes from like random sources. Oh. Yeah. Why there are so many locked words here? Interesting. Alright. These are probably too small. Wolf, vamp. Wolf might be fine. So that's not terrible. It's not amazing. Oh, let's just go and get us a mesh. So Morgan Maguire has a good collection of triangle meshes, and I thought he had a lower resolution, maybe not. Oh, you know what? Maybe we should just do... I think this mesh might be fine, actually. Well, it's kind of high poly, 31k polys. Teapot. I have a Teapot mesh. Let's just do a Teapot. Teapot is like a classical computer graphics mesh. Let's see. Yeah, okay, alright, let's just do this. This is fine. This is gonna be fine. So there is this mesh. It's a lot of triangles for relatively simple shape, and right now I can generate discrete LOD versions of this mesh, and at some point I guess the lid starts to detach itself. Maybe I need to tune the heuristics, but I guess this is sort of inevitable. But it's not too bad. Like from a large distance this would look fine. So the way my algorithm works is, as I said, it picks a lot of collapses to do in parallel. So we will restrict our algorithm to do just one collapse, just one like pass of collapses, so that none of the collapses overlap. Because this is kind of, so I was saying, hey, once you change the triangle once, you can't change it again. And if you want to change it again, you have to take the final mesh that you have after all of these like iterative simplifications and do another round of LOD on it and have another buffer of triangles to render from. So because of that, we will only do one pass. And maybe the assumption is that whoever wants to run this algorithm has to run it in a loop, and each run produces like the next series of simplification, and that's like a next index buffer. Because that's kind of the assumption right now. So this is actually easy. We just replace the while loop with if. Oh, and great. All right, fine. Yeah. So I'll butcher this code a bit. It's definitely not going to be the case that I will just submit this as is. So let's see. All right. So as you can see, this is what one pass of the algorithm does, right? It picks a bunch of collapses, kind of less than I was hoping it would, but why does it not? Interesting. Yeah, it kind of collapses less than I hope it could do in one pass. Let's see why that is. Yeah, it hits an error limit. Why does it hit? Oh. Okay, so the second thing that we'll do is that there is this heuristic. So my algorithm is designed to do one pass at a time, and then each pass does some number of collapses, and it's slightly conservative because it knows that if it doesn't do too many, then the next pass can sort of clean it up. But this actually is problematic in this case. So let's just say that for one pass that we are doing, we will kill as many triangles as we can within the error bound that we are passing to this algorithm, which is done like at a higher level. Like there is a simplify. Yeah, there's this target error thing, which is like some sort of relative area or volume or something that we can compromise. So let's just say that whatever this value is, we'll just collapse as many edges as we can without getting under, without getting over this error, and without removing, without like collapsing edges that conflict with each other, whatever. So to do this, I just need to say that I only need this target error. I don't need this error goal. I don't need this. Do I need this? I don't need this. Hey. Alright. Let's see if that works better. Alright, so that worked a bit better. We are still kind of getting stuck. Right, okay, cool, yes. So this is what I would expect this to do. So it goes from 15,000 to about 8,000 triangles now in kind of one go. The fact that we can do this is interesting. This might mean that I can optimize my other algorithm, but yeah. So if you see what happens here is that for any part of the teapot really where there were triangles that are kind of dense, we removed some edges. And then the idea of my current algorithm is that you can just do this again and again to clean up the mesh more and more. But in this case, we are kind of getting stuck because we have already removed one edge, and my current algorithm doesn't want to touch the vertices, like the new vertex of this edge essentially, that this edge collapsed to, like, anymore. This sliding window LOD algorithm doesn't want to touch any triangles, which is a stronger statement, which we'll get to. But okay, so this is a good approximation. So this is what my algorithm right now, with my restrictions on collapses, works towards in one pass. And these restrictions that I have right now, they are like more lax than what the sliding window thing does, because the sliding window blocks off entire triangles. So I'm expecting that once I implement this heuristic from a sliding window, this simplification will not go to 8,000 anymore. Yeah, also this is kind of why I wanted to have a coarser mesh, because like it's kind of hard to see what's going on here, right? Like there's too many triangles here. Let's do this. Let's simplify the teapot. So we'll stash the thing, we'll run this again. I have a hotkey now that I can use to save the simplification result. So let's just take this teapot, let's like butcher it up to let's see, what am I comfortable with? Actually, yeah, maybe let's do this. So, okay, let's start from here. So this is still a reasonably fine teapot. It has way fewer triangles. It has like 2.5k triangles instead of the 15k that it had originally. So let's save this to a file, and then let's open the file. How do I? All right, whatever. I haven't mastered the communication between this Linux thing and the Windows stuff. So this OBJ viewer, oh, there's no normals. Well, whatever, that's fine. Yeah, there's like now an OBJ viewer built into Windows, which is fun. This is just like comes with Windows 10. This mesh doesn't have normals, didn't have normals originally, so they show up as black, which is not great, but whatever. So yeah, so here's a mesh. So this is like a mini teapot. That we will work with instead. Hopefully that will be easier for us to see what's going on. Alright, so we are starting with the result of like my earlier algorithm, that's just fewer triangles. And now let us see what one pass of the algorithm without error bounds can do to this. Alright, so this is fine, right? So we go from like 2600 to 1400. You see the mesh outline changes very, very visibly, right? And so the idea of this sliding window technique is to try to get roughly the same level of simplification in one continuous buffer, where you can do like one or two collapses at a time to essentially slowly go over from this to this without it being too visually jarring. All right, so that's, oh, what is this? Oh, right, like the teapot I think falls. Oh yeah, right, yeah. So this teapot, the teapot is like hard to do really good simplification for, I suppose, because it has all of these like handles. They're not solid. There's actually two sets of faces, like the inside and the outside. And so what the simplification algorithm can do is can kind of like collapse them inside each other, and then you get them to show through. Maybe if the mesh is far enough, it doesn't matter, right? But also we are kind of ignoring some error stuff that I'm doing now. Whatever, doesn't matter. Yeah, so let's try to change the limits. Let me close this. So let's try to change the limits to do what the sliding LOD technique does. We have like kind of two parts here. So one part is we want to do the collapses as many as possible, but only the collapses that the sliding window technique is compatible with. So never touch a triangle once we have modified the triangle. And the other thing is that we need to, once we have these collapses, we need to create this kind of like interesting buffer where there is collapses that are ordered in a specific fashion. So let's try to do that. I was kind of wondering if I should just make a new function, but I will just change this function and we'll see what happens. And I'll need to extra data and stuff like, anyway, whatever. Okay, so the way we will do this is this. So right now the code says, let me just go to this code. It's here somewhere, yeah. So right now the code says we are collapsing an edge, and these are the two vertices that we are collapsing. If any one of them we cannot move anymore, we don't do this collapse. Otherwise, we do some work to record this collapse, and then we mark them as they can't move anymore. So in addition to doing that now, we'll have to mark the vertices in the triangle. Yeah, we'll have to mark the vertices in the triangles that would change after this collapse as not moving. This will be painful. Let me disable. So I'm like simplifying. This code isn't really built for this sliding window stuff, and this is a prototype. So I'm trying to remove parts that I think will be problematic for me. And this is one of them. Because if I have to deal with seams in this will be hell. Let us just say that for the purpose of this exercise, you know how like we did all of this work, when was it? 2 weeks ago? About collapsing like UV seams and stuff like this. Let's just say that none of this can happen. You know, we live in a cruel world. Actually, borders are fine. Yeah, so we will only collapse vertices that don't have like UV pair problems, because this will make it easier for us to write this code. And then if this code actually works, we'll figure it out. And if this code doesn't work, yeah, so it's slightly worse. It's like 1600 instead of 1400, but that's fine. And it's less aggressive, so it's less bad. Anyway, yeah, because I don't want to deal with like seams right now. I'm not sure this technique, like as I said, I was like kind of interested in this technique. It seemed interesting before I thought about this for a bit. After I thought about this for a bit, the technique seemed less interesting, or like less practical, I suppose. I don't know. So I'm not sure that we'll actually do this. So I kind of want to do like a quick prototype of, hey, is this even viable? So anyway, yeah, so what we need to do is now when we move this vertex, like the orange vertex, right? We have to mark all vertices of all triangles that survive this transition. So in this case, basically, we have to go over like triangles 1, 2, 3, 4, 5. And we have to mark every single vertex of this loop as we cannot touch this anymore. It's done. Because right now we are only marking the orange and green. We can collapse other vertices towards these guys, we just can't move these vertices, right? So we can't move, where's my pen? We can't move this afterwards. we can say move this vertex here, right? So there's multiple ways to do this, but I already have, what I want is I want a structure that given orange vertex can really quickly give me all of these vertices around it. So I have a structure that oh, does it just work? Because everything is manifold. Everything is manifold except for borders. Let's disable borders. All right. So by the way, if anybody is wondering how hackwicks work like this. You're like, hey, I want to solve this problem and I have a week and it's like a complicated problem, and I will cut every single corner I could possibly cut in order to be able to solve this problem. Because at the end, I want a prototype that tells me if the problems like are actually worth solving. And this is how I work for like a week on like new terrain, and then it takes us like a year to ship it, like one person here. And then I work for like a week on lighting, and then it takes us like, I don't know, 4 or 5 person years to ship it. Because you cut every single corner that you could possibly cut to get the result that you think will prove that this is viable. All right, so hopefully this will not... All right, this is still fine. The Smash doesn't even have board. Okay, this is awesome. Yeah, so I already have a structure that can go from this vertex to all of these guys. I was hesitant to use it just now because it doesn't always work for complex topology, and I wanted to do something else. But if topology is simple like it is here, then it works. So this is great. Then we will just say for this guy, so I want to do another... Do I just do this like inside this thing? Because there is vertex count. There's no vertex count here. Okay. All right. So we will pass the structure that can quickly give us the vertices around the vertex that we already use for a bunch of other computations here, which is nice. This structure doesn't survive after the first round of collapses, but the good news is we are only doing 1 round, so it's good. So then I want to have like an extra set of flags to not deal with, some complexity, which is like adjacency locked or something. So this will tell me, hey, can you move this vertex or not? The reason why I need this, whatever. I will not explain why. It's important for me to have a separate thing. There's a reason. The reason is that, I guess, here I'm saying you can't move the vertex. So R0 is the vertex that we are moving. R1 is the vertex that we are moving the R0 towards. This code says, these collapse rules work by saying, hey, you can't move R0 and you cannot move towards R1 if R1 has been touched. And the reason is, oh, maybe I don't need this anymore. The reason is it kind of makes the error worse, but maybe I don't need this. Let's see what happens if I remove this. Do we get like more collapses or not? Because I kind of want... Does it even matter? Oh, I get an assert. Okay, let's not mess with this code. This code is correct as far as I know, and it's important for it to stay correct. So let's just say, yeah, okay. If R0 is marked as it can't be moved anymore, then don't move it. And when we collapse, so here we say, okay, R0 is collapsed towards R1. R0 is the orange vertex, right? So then we want to say, hey, for all of the vertices that R0 connects to, R1 included, right? But R1 we are already marking. But more importantly, like everything else, we cannot move these guys anymore. We can move stuff towards them, but not move these guys. Can't move these guys. Oh, and there's like another problem here. Oh god. This will be fun. Yeah. Alright, that's fine. So the way this adjacency structure worked, I talked about this before, I will not talk about this again, I will just copy some code. I think I talked about the structure in the first meshoptimizer stream. It's not a very complicated structure. Yeah, so we want to go over adjacency stuff for R0. For every single vertex, we want to lock this vertex. So I think this is it. Let's see if it works. Haha, it worked. So we were previously simplifying down to like 1500-ish, and now we are only simplifying down to 2000. So that's, by the way, interesting. Let's do the math. So we are removing like 600 triangles from a 23%. This is amazing. So the article by Tom Forsyth that I just had open. Let's open this again. It says, well, oh yeah, It says, after a while the algorithm simply runs out of triangles that have not already been involved in the collapse, which is what we just did. Most meshes can only lose around 20% of their triangles before this happens. This is why I didn't realize that this restriction was there before, and then I realized it after I thought about this, and it made no sense how the algorithm works, and then I read this, and then it made sense. So this says the most realistically that you can remove out of a mesh is like 20%. Which is what we are getting here. We're getting like 23, right? And after you have removed this, you cannot move any other vertex realistically. So you can't keep like a single index sequence, which is not great. Yeah, so this means that, yeah. So we'll still do this, but yeah, I wasn't sure if on Teapot this is true. This is like not a very good technique. Yeah. Oh well. So yeah. So this means, okay. So this means that if you have where's my calculator? So let's say you have a mesh that you want to reduce like 2x, right? You can only reduce 20% of the time, and the buffer, by the way, will be bigger than usual, but we'll see how much bigger later. So you can do 1.2 in one go, 2 goes, 3, 4. So in 4 steps, you can get down to like half the resolution, right? So if you want to get like if you want to reduce the resolution 4x, you need like 8 steps, right? And this is already approaching, like if you aren't reducing your meshes down 4x, then I don't know why you need LOD in the first place. I mean, it's kind of, you could stop at like 2x, but it's not super great. And yeah, if you're doing this 20% of the time, then you kind of need a lot of memory anyway. So, this is why I didn't like this technique, but I wasn't sure if this 20% number is like on real game meshes with a lot of UV splits, you can get 20% off, or like here's a Teapot that does not have UV data, doesn't have normal data, doesn't have anything, 20% is the limit. Sounds like it's the latter. So preliminary conclusion, this technique is not great, but we'll go through trying to make it work anyway, because hey, we just started the stream. Well, that didn't just start the stream, but I'm just curious if, like, how much work it is to actually get it to work. Alright, so, oh, I'll still need the triangle adjacency. Okay, whatever. Yeah, okay, so, alright, so where we are at right now is that when we collapse an edge, we don't touch It's a relatively quiet neighborhood, but there's like a street nearby that's kind of narrow, and the acoustics is pretty good. So whenever there's a vehicle that's passing by that's like a large vehicle, you know, it's kind of audible. Anyway, right, so where we are at is we can collapse triangles, we can collapse edges, and we only collapse an edge if we have not actually modified any triangles, hopefully, that are adjacent to this edge. At least this is what I think it should work out towards, because we aren't moving these guys, so the triangles should not be modified. So the next step is, right now we are still building like the final simplification. So we are going from 2600 to 2000 triangles in one go, right? And so the idea of sliding window is to not remove the 600 triangles like all at once, but to remove them in small groups at a time, so that you can progressively move through this collapse sequence, right? So let's see how that should work. Let's see how that should work. So reminder, this is like not production code. So because this is not production code, let me just hack some stuff together. Yeah. Okay, yeah, that's fine. That seems fine. All right, yes. So what I want to do is I want to build up like an intermediate thing, which, so normally this library doesn't use STL. Like this library emphatically doesn't use STL. The sample code for this library and the tools around this library use stud vectors, because stud vectors are standard and convenient. Although in the last stream we have ripped out stud vector from the OBJ loader because I was dissatisfied with performance. But this is prototyping. We do not care about performance in this prototype, which means that we will do things that you should never ever do. So I want to fill a buffer that for each collapse that we are doing gives us, what are you doing? All right. Should we just, yeah, it should be just indices. So let's do this, or I guess. So it gives us the set of triangles that were removed and the set of triangles that were modified. Is that good enough? And then kind of for the lapsed collapse, no, we don't need, right, yeah, we don't need like a full triangle, we just need, yeah, I think we just need this. Is that true? That might be true. Actually, yeah, okay, whatever. We will just, this is good enough. So for each, I think this is gonna be fine. So yeah, so for each collapse, we will fill a structure that that tells us which triangles have been modified, and we will use this information to kind of reconstruct this weird index sequence that I was talking about. So this is like vector of vectors, and this is bad for memory, and you should not do this, but we will do this anyway. To get at the triangle, so these will be triangle indices. To get at the indices, we will use a lookup structure that I have in my code someplace else. Somewhere, yeah, which is called triangle adjacency. We'll just boldly copy this code and boldly paste this code here. So yeah, this structure answers the question of, given a vertex, which edges does this vertex belong to? This structure answers the question of, given a vertex, which triangles does this vertex belong to? So, oh, this is called adjacency. This cannot be called also adjacency. So yeah. If I remember right, these are like exactly the same in terms of the interface. Index count, vertex count, index count, vertex count, indices, index count, vertex count. Yeah, okay. So that's like almost the same code, but the data that it tracks is slightly different. So the code in these guys is slightly different. All right. And we want to have. So we want to have this beautiful so normally I would not like intermix output and input parameters. Also, this function is getting kind of long, but this code is a prototype. If we decide that this is a good idea, which seems less likely by the minute, we will refactor this. If we decide this is a bad idea, this means we haven't spent any time figuring out if we need to refactor this function, which is great in my book. All right, so now it should be pretty simple. So we are taking this vertex, we are moving this vertex. All triangles that this vertex belongs to have been modified. That's it. So it's like the same code like it is here. So let's do this. Let's copy this. And I think the structure is the same. It's like I basically built these guys. So this is how you write like C code, right? I mean, like the structure has a constructor, so it's technically C++ code, but this is basically how you write C code. You don't spend time on trying to figure out what's like a beautiful abstraction that, you know, you cannot mess up ever, and then how do you make it really efficient and how does it work, and then it takes forever to compile and stuff. No, you say, hey, for each vertex I need a range of, I need like a micro array of data. So this array will store the number of items in this array. This array will store the offset in a giant array into this data. This means that instead of, like, this is this vector of vector stuff, but laid out in a very efficient way so that it's really fast to access, really fast to build, doesn't require many allocations, etc. So this is kind of how you would like build this in C code. Even if this code seems like it's C++ and it uses a few C++ features. All right, so this is definitely not something that would happen in C code, but hey, it's a prototype. Yeah, so we are just saying, hey, we have, since we are moving vertex R0, we have modified these triangles, the triangles that this vertex belongs to, like these 5. That's it, right? And then we need C collapse results. What did I call it? Results. Right. Yeah. Okay. Cool. In C++ 11, you should probably do this, but we can call it like this. Doesn't matter. Right, so in theory, after this function, we have all of the information we need, because for every triangle, we know which triangles it modifies. Here's an important thing that we can check now. Let's do this. Let's just check if this code even works. I hope this is mildly entertaining. All right, 600 triangles, good. I waved my hands around when I was doing this adjacency locked stuff and said, hey, I'm locking the vertices that are connected to this vertex, which I think should mean that these triangles will never be modified again. Now we can actually check this. Let's check this. I'm like going back and forth between using a STL or not, because like normally I would never use a STL in this code, but since I already started, it's hard to stop. So let's just say, oh, note, okay. Let's just use a STL for a while. So let's see if we should probably yeah. So let's go over the stuff that we have generated here. And I'll start to use C++11 because remember this is a prototype, so this library is not C++11. Oh, it will not build. No, it will. Oh, damn it. Yeah, it will not build in Linux if. But I don't care. That's fine. Yeah, so this library is not C++11, but once again, what do I care now? Like if you're a real C++11 programmer, you would write this, but I'm not a real C++11 programmer. So what we want to do is we want to go through all the modified triangles, and we want to do a few things. First is we want to check that this triangle index is invalid. So the input to this function is not number of triangles, it's number of indices. There is three indices per triangle, so that's what the index of the triangle should be like. So then we should say that the triangle isn't modified, and then we should mark the triangle as modified. And what this does is it kind of cross-checks all of these different arrays together and says that if the triangle is modified in one collapse, it can never be modified again. And if this is true, this means we can build our like sliding window structure, or whatever you want to call it. We didn't hit, oh, we didn't simplify. We did not hit an assert. Alright, good. So we are basically almost done. Well, I mean, it'll take us like half an hour to actually finish this stuff, because even if it actually works, we'll have to write code to make it like show. But we are close. So what we are saying here is that for every collapse, we have a list of triangles that are modified as a result of this collapse. And now we just need to build this sliding window structure that has triangles that are not modified at all in the middle, triangles that have been modified in the like first section of the array in the order of collapses, and then triangles that are a result of this modification that have survived through it at the end. As you can see, the total number of like elements here is more than we started with, right? So like you're saying, hey, can you simplify these 9 triangles? And it tells you, sure, here's 12 triangles. So we need more space. To get more space, we will do something. All right, yeah, so let us build, so this will be, we'll not touch this stuff, but this will be like sliding indices. And also we need a structure that essentially tells us about these ranges for each LOD level. Should we... Yeah, so these don't... Yeah, so we need like 2 integers for every... Okay, let us just... Sliding ranges. So here we'll use 2 integers to describe a range into sliding indices, right? And here we'll just have actual like vertex indices for each triangle. And we need to teach our function to output the second array. So let's just add an output argument. And we will not bother checking like whether we have enough space in these arrays or whatever the case will be. We'll just say that you can't have too many ranges because you're only... Oh. The size of this array actually is pretty predictable. Like each collapse removes... Well, in this world, each collapse removes two triangles, but each collapse has to remove at least one triangle in any simplifier, which means that you can't have more ranges than collapses. And you can do a worst case estimation on this guy as well, because hey, each triangle is only modified once, and your worst case is that you modify the triangle because you need to waste space for the new copy of this triangle. So your worst case, I think, is just that you have 2x more like triangles in this buffer that represents multiple levels of detail. So that's actually slightly less hacky than you would usually do this, which is nice. Alright, so instead of doing this, we'll say, so we will need enough space for 2x the number of original indices, because worst case one triangle is duplicated once, or each triangle, I mean, is duplicated once. And for the ranges, the worst case is that you have like whatever. This is like super. This is not even the worst case. This is just, this will definitely be enough for reasons. And then we'll say, and then instead of oh yeah, okay, that's fine. So then instead of doing what we were doing before, we'll say here's the indices, here's the ranges, and then it's kind of unfortunate we won't just know. All right. And then we'll say we will return the number of ranges, and then we can also even say that the last range I feel like I've said this like 1,000 times on my stream, but this is not how I would normally write this code. Well, I would normally write this code maybe even like this, but I will never submit something like this. Well, and the good news is I won't. So, basically I want to say that the last range, the last element of the last range, so range is a pair, first and last, or begin and end, right? And the last element of the last range represents the furthest index, because remember, like, this the sliding window contains data for the first LOD first, for like the final LOD first, and then for coarse LODs. So the last index that we ever need is the last index that is needed by the last range. So we'll just trim everything else. And this will be useful for us to sort of figure out how much space we are actually spending on all of this extra LOD stuff. Alright, now we need to write code that actually works with this stuff, which is gonna be different from the code that we have right now. So let me just trim this. I don't need this. I mean, this will still work, so maybe I can keep that. Let me flatten. I don't even. How many? There's so many edge cases here that I'd have to think about if I wanted to actually make it work. Let's just say that it's stupid to not. Okay. Alright. Kill that, kill that. I'm basically removing like as much stuff as I can. I don't need this to like make it easier to write the code that I actually need to write. I think this might be it. I don't need this. Okay, yeah, that's fine. All right. Oh no. Oh no. Seriously, there's like no warning on this? Maybe our code doesn't work, which is unfortunate because we have already butchered the code. Alright, so let's see. So right now my code will compile but not work because I'm returning 0 ranges. Oh, and also for other reasons. Yeah. This is painful. Alright. Damn it. So yeah, so basically it looks like the code that we wrote to validate that the... Alright, the code that we wrote to validate that the modification arrays work didn't actually validate anything, which is not great. And we have already butchered the interface and some of the rest of the code. So we will have to figure that out. So, alright, yeah. So, I short-circuited the whole thing to like return 0 ranges for now, which the outer code says it's not cool, which is fine. So, how come there is no warning for this? I mean, okay, I guess this is hard to give a warning on. Okay, man. Alright, would have... This is just bizarre. Okay, is there like a warning here? There's no warning here. So you're saying I can like write something like this and then just be like, hey, like, this is really... Oh. There's still no warning. There's like 4 unrelated... Oh, no, wait. Yeah. Like, there's no warning on this line. Alright, so I'm disappointed in Microsoft Visual Studio yet again. I think Clang works on this. Doesn't Clang warn on this? There's some comments. Alright, let's just brief digression, because I'm kind of upset with this thing. I don't know, I don't even care, like void foo. So in Clang, if I do like this thing, and then like what happened is I wanted code that was like this, and then I forgot this part, and then there's like no warning. Is there no warning here as well? Oh, hey. Statement has no effect. Yeah, so this is the warning that I was hoping to get from Microsoft Visual Studio. I did not get this warning, which is not great. Alright, yeah, I'm dearly hoping that my code still works. Let's see if that's true. Oh, now it says unreferenced local variable. Well, that's okay. Let's see. Alright, yes, so our validation code still works, it's just that we are still returning number of ranges. Okay, thank God. If I had to like debug this other thing by now, it would have been really painful because I already like removed a bunch of code that was necessary. Alright, alright. So we are good. Let's restart, recover. So we have a bunch of collapses. For each collapse, we have a bunch of triangles that are modified. This code successfully now checks that if a triangle has been modified once, it is not modified again, which is good. Now we need to collect all triangles that have been modified, which includes removal, in the first section of this array. And then we will need to and then we'll need to put all of the stuff that we haven't touched, which I don't know actually how many triangles we have like that, but we'll see. And then we'll need to put the modified triangles at the end of the array, and then hopefully stuff will work. So let's just do modified count here, and modified count plus plus, and and modified here, I'm playing a bit loose with the terminology here. I'm saying modified and removed, removed is modified, right? I didn't want to split them into separate arrays, which is probably fine. So let's do this. Let's do this. Not enough arguments passed for format string. Indeed. In some cases, the warnings help. In some cases, they don't. So this is why we got stuck, right? So we collapsed 300 edges, which means 600 triangles, because each edge is one triangle in the setup. Sorry, each edge is two triangles. Each edge removed triangles. And then we modified or removed 1600 out of 2600. And I guess all triangles that we haven't modified, they lie on the boundary between multiple other modified triangles. So it's just not possible to do anything anymore. So this is kind of why we got stuck at 20%, right? Which is expected. What can you do? All right, so now, so here's how it's gonna play out. So this is wrong. Let's just say that we have to collapse something. This is not always true, but I don't want to deal with the edge cases. I don't need this even. And yeah, so the way the code worked before is that there was this function that took a bunch of indices and then just changed them to either remove triangles or to change the triangles in place. But this scheme is different. This scheme wants to preserve everything carefully. So we can't use this function anymore, and we won't use this function anymore. Instead, we'll just fill things slowly and carefully and meticulously. So the way this array is gonna work is that there is 0 to modified count -1 elements. This is modified triangles, right? Then from modified count to something, this is unmodified triangles. There was 1,000 or so of these, right? And then there will be results of modifications at the end. It is kind of important to know this X thing. So I think basically, let's just say, okay, unmodified begin is modified count. And I'll have to be careful. These are, let me just do this like this. So we have 3 indices for every triangle. So we start writing unmodified data from this index, and we have, all right, so we have total index count indices. If we do this, oh, this is just, oh, never mind. Okay, right, yeah. Yeah, I guess as was obvious in this example, we are starting to write modified triangles after the kind of last triangle in the original set. So yeah, so this is the range in the output index structure where we will just dump triangles that have not been touched. After this value, we will dump triangles that are results of modifications. So now it should be simple. We'll keep like right modified 0 says t right altered 0 and right unmodified. So this guy starts from unmodified begin, and this guy starts from unmodified end, and this guy starts from 0. So we have 3 right pointers. So let me I'm feeling good about being able to actually finish this and have it work. So let me very briefly say what I'm doing actually. So the sliding window technique has 3 parts in the array. There is 1 part in the middle. This is unmodified. Oh god, alright, let me just actually try to write words that are legible. So this is unmodified, this is modified, and this is, we'll call altered. Like these are results of modifications, right? I'm expecting that, so this stuff just is verbatim copies from the original array. Triangles, we can't do anything anymore. So this is stuff that we will be removing from the mesh. And this is stuff that we'll be adding to the mesh instead of the things that we have been removing. The amount of altered triangles should be less than the amount of modified triangles, because we are either removing a triangle or changing a triangle. We are never like adding a new triangle just because we want to. And so we'll just keep 3 right pointers here, 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 and then we'll just move to the right, and then this guy should end here, and this guy should end here, and this guy should end here. And we'll actually be able to assert. So we'll have some loop here that like does something with triangles. Is it gonna... How am I gonna... This guy... So this guy is a bit sketchy. No, like this guy is a bit sketchy because I can't go through... Yeah, I didn't want to go through triangles. But that's fine. It's gonna be fine. So yeah, at the end of this process, we basically are hoping to say that the right modified ends up at right, like whatever the next one is, right? And then unmodified gets all the way to altered. And then we don't know where altered ends up as, but this is the thing that will be the last range. Oh, and also we need range count. What's the range count? Right, so, okay, so that's fine. So we will add, yeah, okay, cool. Alright, yeah, so I have a good idea. So the first range that we will write into our output array is the range that's the original mesh. So ranges, range count times 2 plus 0 is gonna be 0. And this is a pair, right? You could use like stud pair, but, and I guess I'm using a lot of standard library in this stream as well, but whatever. This is how I would have written this code if I was to actually ship this code. And then this is where the range ends, right? So the first range is just, and then we need to do range count plus plus. So the first range is just where the original mesh is, right? And then for each collapse, we will right triangles here, and then add a new range. And then we also need to write unmodified triangles. And we'll do this kind of in 2 steps. So the first step is we'll go over all the collapses that we have. And for each collapse, we want to write one new range that removes a bunch of triangles and kind of adds a bunch more. So we are going through all triangles that have been modified. And then we need to first we need to just write the data for this triangle into the kind of unmodified. It's kind of weird. Modified and altered are like synonyms, right? So whatever. I hope people are mostly getting what I'm doing. I think I am getting what I'm doing, which arguably is the most important thing. So yeah, we will do this. So first we'll just copy the triangle verbatim from the source index array into the modified part, and then we will have added this. So this is the triangle that we had to begin with. Now there's two cases. For the triangle that's like the result. Oh, actually, let me. This code is already like here, so I can just snatch that, and we can do. Alright, yeah, so this is the source triangle, and then we wrote the source triangle in this first part of the array where the original triangles belong. And then we've incremented the right pointer. Then we say this is what happened to this triangle after the collapses. This is the new triangle. We can keep this, whatever, we'll keep the assertions. So then there's two cases. One case is all three new indices of the triangle are different, which means the triangle has survived the transition. There's another case, which is that the triangle is degenerate. For example, one index is the same as some other index in the triangle. This means the triangle got removed. The good news is we don't need to do anything with these triangles. So, but yeah, if the triangle has survived, then we need to write it to the right altered portion. And we have written this, so we'll increment the thing. All right. So this covers the modification state. Now we need to output the ranges. So the idea is that the range. So we want to record the range after the collapse, right? So we've done a bunch of collapses. Now, how should you draw the? We could do it before collapses. Whatever. No, yeah, we can't really. So, can you? Yeah. Okay, this is the right thing to do. So the question is this, right? What's the range in this mesh that represents the state of the mesh after this collapse? Well, it's easy. This stuff that we were writing, these are triangles that were in the mesh that were used before this collapse happened. So we don't need to include these. So this means that we need to start our range at the new value of right modified, because that's kind of where this pointer ends up at, right? And then the last element in the range should be where this pointer ended up as. So I think it should just be basically, you know, like this, where we start at right modified and end at right altered. And I think this is it. And then the other thing that we need to do is we haven't done anything with the unmodified stuff. So these loop only process triangles that we have touched, and we have to copy the triangles that we have not touched in the destination array. So let's just go over all of the triangles. There's no, okay, like this is like not a great way to write this loop, because if the compiler isn't super smart, or if you're in debug mode, this division by 3 will happen on every loop iteration, but in release it doesn't really matter. And this is a prototype, so I don't really care. Why should I care? If not modified flags. So yeah, we just need to copy essentially all triangles that have not been modified into come on, what is going on? So we need to grab the 3 indices and just copy them into, oh wow. Right, unmodified. So I think we're done. We don't have code that like renders the thing that we have just generated, so I have no idea if this code works. But hey, I think we have done everything that we needed to do. Right, modified, doesn't think so. Oh yeah, this is like, okay, this is like, alright, this is a stupid way to write this assert. I mean, I could technically, alright, you know what, yeah, so these assertions are wrong because they want to ask, they want to check that the value of this guy after everything that we have done is equal to the value of this guy before everything that we have done. But that's not what the code is doing. So realistically, basically, I need to do this and I need to do this. This is the correct way to write this assertion, hopefully. All right, we don't have any assertions. This does not mean the code works. And you know, you can see that like we aren't rendering the results of our work, right? So this is why the technique, let me just double check that nothing is really bad. All right, nothing is exploding yet. So, so I think we have generated the data that we need. Oh, we can put a breakpoint somewhere and actually figure out what's going on. This is nice. This is gonna be nice. Let's put a breakpoint here. There's a beautiful technique of putting a breakpoint on the line where you cannot put a breakpoint. Oh, I could have. Whatever. Yeah, I didn't need to do this. I could just do this. Oh, but I don't know what. No, yeah, it's all good. So let's check. So here's what we've done, right? So we have this like semi-complicated algorithm. We hand-waved around a bunch of stuff with like UV mapping and stuff. All of this can be resolved. It's just I didn't want to figure that out on stream. There's like data structure questions. It's not really data structure, I guess. It's just that the parts of the algorithm need to be like tweaked, right? But what we have is a function that can generate us a large array of collapses in sort of one go, as many as it can possibly do within the target error. And in theory, we can render these like meshes after collapse one at a time. So in this case, we have nothing. Oh, this is right. Sorry. Okay, now we have something. Right. So we have 300 collapses, like 600 elements in the range array, which is there is a pair for every range. So we have 300 collapses. So in theory, this array represents 300 LOD levels, but each LOD level is only so slightly different from the previous one, right? You'll notice that we had around 8,000 indices in the original array, and we have like 11,000 in the new array. So we are using more data than the first LOD level, but it's less data than what we would have needed if we wanted to actually represent these like 300 LOD levels or even like 30 LOD levels as separate arrays. So that's nice, if the code works, which we don't know yet. So now all we need to do is we need to write a function that like renders the thing, right? Since we aren't using, let's do this. Since we aren't using this right now, and we aren't really using this for all intents and purposes could be like 0, because we are trying to simplify like as far as we could possibly go. So we might as well just do this when we open the mesh. So right now when I start, it will generate all of this data. And now we just need to write some code that can render a specific range and see if it works. So let's write this code. Where should that go? Should probably go here. Yeah, it should probably go here. So yeah, let's just say, hey, we want to render this range, right? And wherever, do we like zero initialize this thing? How does this code work? Okay, it's a global, so that's fine. So let's just say that when you press like left mouse button or right or left, alright, left, just left, not left mouse button. So when you press left, we'll be like, hey, options range minus minus, well, if options, whatever. Options range minus minus, redraw true. Also, I'd like to like output the thing. In the title, so that we know which range we are drawing. Oh, we won't know which. Alright, that's fine. So yeah, it's a prototype. My demo program, like this demo program, it can technically work with more than one mesh, and I sometimes use this, like it shows different meshes side by side, and I can simultaneously simplify them to whatever. But at this point, I don't care. So we will say that there's only one mesh, this one, and we'll constrain this thing. So if like f LOD mesh, oh, all right, yeah. So adjust the thing, and then options range stdmin, options range, so there's like 2 integers for every range, so this is what the range count is, and then we'll just say that we'll clamp the thing to like a valid range of ranges. And then we will say that we are drawing something at range with this number of triangles. The number of triangles is so yeah, so the number of triangles is like the size of the range, which is just the distance between the end point of the range and the begin point of the range. So it should be like FLOD mesh sliding ranges, range times options range. Oh god, all right, this is gonna be long. Why does it says T? Okay. Plus 0, plus 1, minus. You'll notice that I often write plus 0, like I did this a bunch of times here. And this is just for symmetry. Like it's easy to visually scan this and say, hey, 0, 1, 2, 0, 1, 2. Like it's harder to visually scan this and say there's nothing here. Is this right? Oh, this is 0. This is good. So yeah, I like writing +0 in cases like this. And this is the the size of the ranges and indices. So this is technically, it should be divided by 3. All right. So let's see if that. So we aren't drawing this yet, right? But we are like adjusting the range. There's some warnings, whatever. Aha, right? So now, oh, this is awkward. It doesn't do key repeat. Why doesn't it do repeat? Oh my. How do I do repeat in GLFW? Oh, there's probably, is there like a GLFW? Oh, GLFW repeat. Amazing. All right. Yeah, okay. So basically, I need to move this here and say that if action repeats, just GLFW repeats. Is this even the right thing? All right. So we aren't rendering the range that we have selected, but we are selecting the range and calculating the number of triangles in this range. All right. Yeah. Now I can just like hold the button and then it goes through the range. It's not super fast, but we only have like 300 collapses or something, right? So this is where we stop. And then you see the number of triangles. Now, like, we aren't rendering this yet, right? But we will just now. So let's do this. Where are we rendering this stuff? Here. So yeah, so we'll skip this code. We'll just look at this code. Yeah, okay. So this is like super simple, right? Oh, well, yeah. So instead of going through all of the original triangles of the mesh, we will say that range begin is mesh sliding ranges options range times 2 plus 0. And so this is why this like breaks visual alignment. I don't know what to do with cases like this. Let's do this. So yeah, like that should be it. I don't know. We might be done. And then we need to iterate through this larger array sliding in this. What? Wow. Okay. All right. Let's see if this works. Oh my god. This code works. So, right, so you can see, I'm not sure if video compression like destroys this or not, but you can see that we are doing like small alterations. I'm holding the like left arrow key button, and some of these changes happen on like the other side of the mesh, so you can't really see them. Oh, should we do like 10 at a time? Well, yeah. We can try to do this on another mesh now. But yeah, like so in wireframe, right, it's clearly obvious that we are removing like a few triangles from the mesh. And so this is kind of nice. We are not using that much memory for this. To put this in perspective, let's put this in perspective. So we are starting with, let's do some math. So we are starting with like 2640 triangles, right? So this is 2640 times 3 indices, whatever that ends up being. And we end with, let me wait while it collapses this stuff. Patience is key. We end with 2030 triangles. Which is this, right? So if you stored the original mesh and the first LOD level separately, you would need that plus this, which is what, like 4670 times 3 indices. So this is if you just wanted to switch from like the left, like the original thing to like this thing, right? Let me do the reverse without wireframe. So you can see the silhouette changes a bit. Like if there was a texture here, or like if there were intricate normals here, that would have been a bit more apparent. We'll try to run this on some other mesh like now and see what happens. But yeah, so instead what we see is that, let's print out this stuff. Like here. Well, the number of range is the same as number of collapses, but we have right altered. So this is the far, like right pointer, the right pointer. 3, 6, 80 triangles, right? So instead of wait, this is indices. So instead of using like 4600 triangles, we are using 3600 triangles to represent a continuous transition from 2600 to 2000, right? So like we are still burning a bunch of memory. It's what, like almost 2x. Oh, and we also need the range data. So we had like what, 300 collapses. So that's like 300 times 2 range indices, right? So basically it adds up to like around 2x more index data, give or take, versus the original, which for a 20% reduction isn't amazing, but it is better if you wanted to do like the 20% reduction increments, like one at a time, right? So yeah, so basically we are saying that one pass of this technique reduces 20% triangles and requires plus 100% of original index memory, right? So for just 1 or 2 levels of simplification, this is like reasonable. Yeah, the problem is 20%. Like the way when I was not reading, I guess, like when somebody mentioned this technique to me, and I have read about this technique like 10 years ago, and I had a very, very vague like idea, and my mental model is, wow, okay, like here's the giant mesh, and then you just do the sliding window thing through the mesh, and it just goes from point A to point B regardless of how far these are. And this felt amazing because, hey, and I didn't remember the detail about the fact that you can only do up to 20% and then you have to restart the process. And so yeah, this is why I was like, hey, yeah, like it's a bit more index data, but it's a continuous transition throughout your entire mesh. Turns out 20% at a time is the most you can get. Let's test one more mesh. We're doing pretty good on time. So let's test one more mesh, and then I'll read questions and then talk about whatever you guys want me to talk about for a bit, and then we will end the stream. So the good news is we have code that works. Oh yeah, let's first save this. Alright, so there's like a bunch of stuff. So simplify, manifold only, single pass sliding window works. And then I unfortunately have to do git stash apply because git is weird. Alright. Alright, so what other mesh should we try? Let's see. Like, so the problem is, right, it's only up to 20%. So this means if I try a large complex mesh, then you guys will see no visible changes, because it will like simplify a few triangles and it won't really do much. So I have to pick a small enough mesh, and I don't know what half of these meshes are. Or actually, I mean, it's half is like, I don't know what almost all of these meshes are. So there's that. So it's not easy to pick something that, and some meshes just have like a lot of other issues that I don't have solutions for yet. So we were dealing with mini teapots, so we should pick something that's like, should we pick a lamp? I was really hoping for an Arctic. Oh, yes, okay, I know, yes, let's pick the fox. The fox felt like an optimal mesh. So the problem in the fox is the fox has normals that are faceted. And faceted normals don't work right now at all with my, like, they just like the mesh doesn't get simplified. But the good news is I can just kill the normals. Well, I guess then the mesh will not be yeah, then the mesh is, well, whatever, that's fine. Let's see if, alright, so the technique clearly works. Okay, yeah, so here, let's see how far we got here. So this mesh is a bit more interesting than the teapot. It has UV splits. We are currently ignoring UV splits, but still, and it has fewer triangles, right? So we got to 1458 from 1782. 20%. It's kind of amazing how close the number is to the actual reality. Can I? Yeah, so you see it's been simplified, sort of. It's not too far, 20%. So like the production implementation of this, after you clean up all of the stuff that I did that I wasn't supposed to be doing internally, looks like this. You take this function that does a one pass, and then it gives you a mesh that's like 20% simpler, and then you run it again, and again, and again, and again. And I think we said that you need to run it four times to get to half the triangles. So you run it like 8 times to get to like 1/4 of the triangles or something, and then you get what, like 8 index buffers, and then you waste like ballpark 5x more memory or something, 4 or 5x more memory on index data, but you get a continuous, like, from baseline to a quarter of the baseline simplification. So for what you are getting, it actually works pretty well. I am just slightly upset that it's only 20% each time, which means the technique is not as useful as I was hoping it could be. Yeah, alright, so that's kind of what I had. The good news is the code works. The bad news is the code could have worked better, but what can you do? So I will now read the questions, answer the questions. If you guys have more questions on what I was doing and what I was not doing, just ask whatever. Whoa. I can't scroll the chat back to the very beginning? Really? Wow. Okay, I can scroll it back here, just not there. Oh, never mind. Programming at 11:09 a.m. Yeah, so it's like 10 a.m. for me. I'm never sure when to start the streams. The reason I'm trying to do the streams sort of early, I mean, so like I did a couple of streams late evening, right? And there the assumption is kind of you're capturing west coast of US. Everybody who's East Coast, I mean, if you're like lucky, I started at like 7 p.m. So I guess if you're in New York, it's still 10 p.m. So if your bedtime is like at midnight, then you're still okay. But otherwise, like, you're just not watching the stream, you're watching the recording. And yeah, if I stream, so right now it's like 12, right? So this means it's evening in Europe. in large parts of Europe, it's now like 10 p.m., 11 p.m. in some parts, like 8 p.m. in some parts, stuff like that, which is still pretty good. So that seems like an optimal way to get more people to watch the streams, even though in general it looks like basically I get like 10x more views after the stream than I do on the stream. So not a lot of people are watching the stream concurrently. So maybe this doesn't even matter. I don't know. Right. Yeah, I live in PST. No comments on IQ. Dynamic grass prototype never made it to Roblox. It will. I don't know when. But yeah. I mean, I'm kind of hoping. No promises. But I'm kind of hoping next year. But we'll see. Lava prototype, yeah, not, I don't know, that might not happen soon, not sure. I don't have a favorite color. Also, I remember this question. This was a question last stream. Opinion on Convex Hero. I don't have an opinion on Convex Hero. That's a weird question to ask. No dark theme. Oh, like in Visual Studio? Yeah, I don't know. So, as you can clearly see, Vim is using a dark theme, although I guess I don't know what dark theme people usually use. Yeah, I've kind of used Visual Studio for like, I don't know, like more than, like around 15 years, say, circa 15 years. And I've kind of just like always used the white theme. I've kind of always used the default theme. I think I tried the dark theme and I wasn't like a huge fan. Let me try this. Where is this? Oh yes, it's here. So this, right? Is that what you guys are talking about? Yeah, I mean, I guess it's not too bad. Oh yeah, right, like, so one thing that bothered me is this white bar in the bottom, which is like an extension that I'm using. And I think I looked at changing that at some point. Yeah, I don't know. I mean, this is not bad. I just kind of don't mind the white theme too much. But I can try to live with the black theme. I think when I used Visual Studio Code, that defaulted to dark theme. That's probably similar to this one. And then I just never switched. So I guess it's just mostly never switched. In Vim, I had to switch. The default theme in Vim is like really bad. And this theme is really good. I think this is Monokai or Molokai or something. I think Molokai. So yeah, I don't know, this is not bad. This is not bad. Maybe I'll try this and see how it goes. Yeah, I don't really have, I know people have like their eyes get strained when they look at the white screen. And I don't seem to have too much of that so far. I worry that I will get more of that as I age. But it's not too bad for me so far. Can we get Shiner banned from this chat? I don't know. Too late for that. Still daytime. There's Vim for Windows. Yes, there is Vim for Windows. I use Vim and Visual Studio interchangeably, but inside Visual Studio it's still Vim. I don't know if it was apparent when I was like editing stuff, but yeah, like if I was changing like this code and I wanted to like change this mode texture thing to mode normals, I would do like FT, which jumps to texture, and then I would do CE, which erases it up until the end of the world, and then I can type, and then just type normals. So yeah, I like Vim. Maybe it's not even a matter about whether I like it anymore or not, it's like a drug. So I started using Vim around, I never really got Vim, and then I sort of made a conscious effort to start using Vim. I think this was around 10 years ago. I don't know, I don't remember exactly when, but I want to say it was like 9 to 10 years ago. And I kind of struggled through this, and I used like GVim, right, and I struggled through this, and then I kind of got used to this, and then I got hooked. And now I cannot use a text editor that is not Vim for more than like, you know, a few sentences, except for when I'm writing text. Like free form, like article, I feel happy writing in Google Docs or Word or something where you're just like sort of typing, and you never, Like, I guess when I'm editing text that's like free form, I very rarely go back and edit it. Or I do this sometimes in like one pass or another pass, but it's not like, oh, I typed a bunch of stuff, or wait, like there's a problem here and there's a problem here, let me go back and correct it and stuff like this. Which in code happens all the time, right? Like code for freeform text that I write, it's like several passes through the entire thing and then I'm done. And then code is, there's like hundreds of passes through every single line, over years of maintaining this code, right? So it's a bit of a different paradigm. It's little AU, it's modded. Oh, hey, modded. Why have 30 LOD levels when you can have 300 or 3000? Exactly. So you have like 300 right now that just get you to 20% fewer triangles. So yeah, if you have like, if you do this several pass stuff that I was talking about, then you can have more. Yeah, GLFW repeat was like a weird macro. This is why I was like, is it key repeat? Is it action repeat? Wait, this is just repeat? Like there's a GL underscore repeat. GL is famous for this stuff. Like this is one of the things that they fixed in Vulkan. In GL, there's like GL underscore like random English word. And then you never know the context of this thing. In Vulkan, it's like verbose, but in Vulkan there's like VK, like depth, state, comparison, less, instead of VK less, or something like this. And then you always know the context. So yeah, GLFW repeat is not like a great name. Oh, apparently my computer fan were loud. I don't have, this might be a car. So my computer does not have a fan. I'm streaming this from a Surface Pro, which does not have a fan. My model doesn't have a fan, at least. What's interesting is my Wi-Fi router somehow has a fan. It was acting up yesterday. I should get a monitor so I can read chat. I have two monitors. I have like an external monitor, but I have them in duplicate mode so that I can draw on the other monitor. So like right now I'm drawing on another monitor. This is not a tablet. I mean, it's like a Surface Pro, so it's hard to know what it is. But yeah, I don't, my primary monitor is kind of large. Alright, wait, why did it scroll back? Okay. Ninja is better at coding. Alright, good for Ninja. I don't even know who Ninja is. Why not just use git bash? I mean, git bash is like Cygwin or something like this. This is like full Linux. This is like, there's like apt and everything works exactly like it does in Linux, pretty much. Like I can do, I think I did this before, but I can do like GDB, and then I can do TUI, I think TU enable, and then I can do like bmain, and then I can do like run, and then like this is like full Linux, right? There's like, it's not like a weird, it is like an emulation sort of, but it's done at such a low level that basically everything works. So yeah, I'm not a fan of Cygwin, never used it, and at this, and like after this Windows integration for Linux, I just never will. I don't know. I mean, like I technically use Cygwin, but I never used it in how do you exit GDB? Alright. So yeah, so like I used Cygwin, but I never used it as a primary development environment and never will. Do you think I'm going to have fun with the ray tracing tech offered by the new cards? Sounds like one of those things that'd be fun to mess around with. Yeah, so I'm streaming this from a Surface Pro, which is part of why I've been delaying the Vulkan streams, because Vulkan doesn't really work out of the box, and I think I can install newer Intel drivers, but I'm like not sure what that will do. I might try, I'm not sure. So yeah, so basically I need a desktop computer, and I have been waiting for RTX announcements. RTX has arrived, now people have benchmarks. I initially thought that I would just like go crazy and get a 2080 Ti, but it looks like 2080 Ti is like really expensive for how much performance it gets you, and it's the same feature set. But I am really interested in the feature set. I like the ray tracing stuff. That's like interesting to experiment with. I also like, there's like, ray tracing is kind of cool and interesting, but ray tracing is this weird technology of the future, who knows. There's this other thing that they do. So there's a Turing white paper. All right. So there's a PDF from NVIDIA on NVIDIA Turing GPU architecture. It's kind of like, it's not too in-depth, but it's not like layman terms. Somewhere in the middle. They talk about some stuff that they have shipped. So I'm interested in the ray tracing stuff, of course. Also, I'm interested in... So yeah, so that talks about ray tracing, and it talks a bit about how ray tracing works somewhere. But yeah, so the other thing that I'm interested in is oh right, so yeah, so the other thing that I'm kind of interested in, I want to play with like machine learning and deep learning stuff, and RTX has tensor cores, which presumably means that in TensorFlow and other machine learning frameworks, at some point, not like today, but like in a few months maybe, whenever they support the CUDA 7, whatever it is, it will get faster at training and inferencing, so that'll be fun. And you know, I could get like a Titan, but Titan is really expensive from what I remember, so that's not awesome. And yeah, so this is the other thing that I'm really interested in, and I might actually do, like if I get this computer, I might actually, and I get into the whole Vulkan stream stuff, I might stream that, because that's like really cool. So they have a new rasterization pipeline that's like not based on traditional vertex shader, geometry shader, tessellation stuff, but it's like more manual and low level, and it's very similar to what people used to do on PlayStation 2, and I caught like a few months of that back when I worked on console games like 11 years ago. Yeah, like around 11 years ago, I had like a few months when I actually wrote some stuff for PS2. So that could be really interesting, because that's like that's like an even more programmable way to drive the hardware from what we have now, and it's like half the shader stages, so they killed like 4 shader stages and replaced them with 2. The old pipeline is still there for you to use, but that's like, I'm really curious about this stuff and I kind of want to play around with it. So yeah, I think basically I'm gonna get an RTX 2080, probably not 2080 Ti, because that's really expensive. And yeah, play with that. 15 years ago, when the white was the cool color, yeah, like 15 years ago there was no white theme, like everything, no dark theme, everything was, yeah. Debian VSL app, try, yeah, I don't like Linux X server stuff at all. I like Linux command line. I'm super not, like whenever I try to use Linux, it's like not very awesome. Am I Russian? Yes, I am Russian. FIFA soccer flashbacks. FIFA soccer flashbacks. I worked on FIFA, but this was definitely not on PS2. I worked on FIFA on PlayStation 3 times. I forget if I'm like credited on this. I think I might not be, but yeah, I worked on FIFA Street. How was it called? I think it's just like FIFA Street, but it's a recent. Oh yeah, FIFA Street 4. Did they have a 4 in there? But yeah, so I worked on this game. That was like a reboot of FIFA Street franchise. Here I've spent like a lot of time on this, like 8 months or so. And also I worked on FIFA Euro 2012. So that's a DLC. Not a very good rating, but hey, I worked on some optimization, performance work on this. And I've worked on FIFA 2013 for a few months, 3 to 4 months, and then I went and joined Roblox, and the rest is history. No, yeah, I joined Roblox in 2012, in August 2012, so it's been basically 6 years. Yeah, so FIFA 13 released in September. So I think they messed it up, and I'm kind of like not super happy about this. So I worked on FIFA 13. FIFA 13 had a bunch of work that I have done on FIFA Soccer, FIFA Street 4 that they integrated that, in my opinion, made the game better. So they did, I guess, right. So like there was some lighting work that I've done. There was some crowd work that I've done. There was like lens flares. And I think, so I left EA. So this is September. I think I left EA, I guess it was mid-2012. Yeah, but basically it's like I worked on a bunch of tech on FIFA 13, but I didn't stay there up until they shipped it. And I think they just left me out of credits, which is like not a very nice move. But I mean, this is EA, so why should they play nice? But I think at least I'm credited on FIFA Soccer, FIFA Street 4. Maybe. Let's see if this is true. I think they butchered my name somehow. Are there like credits here? Crazy credits. Alright. Whatever. Just trust me, I worked on these 3 games. Yeah, FIFA 13 on PC. So, yeah, I think on 13 I mostly done... What did I do on 13? Yeah, I think I mostly did not do PC work on 13. I did console work on 13. I mean, a lot of this code is shared. So yeah, that's not a fan. That is a car. But I didn't work on PC specifically. I worked on some PC stuff for, I think, Euro 2012, but not too much. Alright, let's see, a couple more minutes to answer like 1 or 2 more questions, and then I will go. And yeah, obviously, as usual, this video will be on YouTube. Hopefully I will listen to parts of the video after I publish it. Hopefully the sound was alright. If the sound was not alright, then either I didn't buy the right mic, or I just suck at like setting mics up. Do I use Discord? I do use Discord. I forget. I don't really know how Discord works. Like, I have an account on Discord, and I think it's ZuxG, but they have like a hashtag number after the account name, and I don't know if that's like an integral part of the account. Picture-in-picture become a thing for Roblox. I sort of maybe have an idea of what you're talking about. Not soon. Yeah, I have an idea. We're doing something sort of semi like this, but it doesn't enable picture-in-picture quite yet. So not yet. Let's see. Oh yeah, this was a cool thing. Oops. Let's simplify one last mesh and then we'll end the stream. Because hey, that's what we were doing the entire stream, and we only tested on 2 meshes. Let's see if this works. So from 1076 to, so that's also around 20%. It's so interesting that this 20% number, yeah, like 21, it feels fundamental. It probably has something to do with the topological constraints that are, so I think I talked about this sometime before, where most meshes that are real, they look like a lot of grids, like this. Or, I mean, there could be like a different arrangement of triangles, but a lot of meshes are like, if you look at a specific section of the mesh, it's like a microgrid. And of course, it's not like square and it's complicated, but that's how a lot of parts of the meshes look like. Yeah, and so if you took this vertex and collapsed it onto this vertex, and then you said no triangle here that like connects to this vertex can change anymore. What happens is there's on average, and I think I covered this before, there's on average 6 triangles in meshes like this for every vertex. It doesn't mean there's like 6 more triangles than vertices, but it means that each vertex belongs on average to 6 triangles. So there's 6 triangles, and then each collapse removes 2, like this 2, right? And then I guess it modifies the rest, which is 4, and it locks them. And then maybe 20% is just the result of, like, if you do the math here, then maybe you end up with 20%, I don't know. You have to factor in like some other stuff to actually compute this, so I don't know how it ends up being. But yeah, it's surprisingly consistent. Well, we tested like 3 meshes, but we got 20% to do a single pass of the simplification in all cases. So that's fun. Oh, and the other thing that I kind of talked about, I think, is that, yeah, like these rules are a bit too aggressive. It's interesting that it doesn't even touch the... Oh, yeah, okay, never mind. Yeah, so, like, these collapses are more restrictive than they usually are. So the results, like, this end result is not the optimal result with 882 triangles that you could ever get. Like, we are trading a bit of quality for this ability to do, like, from 1076 all the way down to 882 one by one, or like a few triangles at a time. Alright, if you wanted to add a user, you need to type this username and their discriminator. Yeah, so I have no idea what my discriminator is. Let's find out, shall we? I'm just trying to think, is there anything? Alright, it's probably fine. Let's just see. 9414. 9414. So that's me. Yeah, so I'm not. I'm pretty sure I'm not credited in FIFA 2013, although I did work on this. All right, cool. Thank you guys for being on the stream. This was fun. And I don't know what next stream will be about. It might just be that I will stop doing meshoptimizer stuff for a bit and start doing Vulkan stuff. I don't know when that will happen exactly, because I'm not sure if I want to try streaming Vulkan stuff to start with from Surface Pro. And so the good news is I know exactly what computer I want to get now, so it's just a matter of me ordering the parts, waiting until they arrive. Oh, the only problem is, so like, this was ridiculous last time I looked at this. Like, isn't MSRP for 2080 like 700 something? Oh yeah, there's like a gigabyte version. Alright, so this is slightly less bad than it used to be. Why is there a 1-star review? There's one 1-star review? Nobody will buy it for the price of 2080 Ti. Even at 800, that's still too much. Yeah, whatever. Like, I thought the MSRP for 2080 Ti was like 1300 or something really crazy like this. And like, no, I am not buying. If Nvidia wants to send me a GPU, I will happily accept it. But I am not buying a GPU for 1300. That's just insane. I mean, it's not like I don't have that kind of money. It's just like it's not worth it. I don't know. I just don't want to do this. But yeah, so this is not... Oh, this is like out of stock. Fantastic. Yeah, so there might be like issues with getting a 2080, but I don't want to get a different card now. Like, I don't want to get 1080, because 1080 doesn't have the new tech that I want to play with. What's 1080 Ti? Yeah, so that's... Right. Yeah, so like for around 700 I would just get 280, but... Or even maybe... Yeah. So basically there might be supply shortages on 2080 for the next few weeks or more. And if they continue, then I might try streaming Vulkan from Surface Pro. Alright. Yeah, so it's like 30... Yeah, so 2080 Ti is like 30% faster than 1080 Ti, give or take. And I do want RTX. I don't want to get 1080 Ti at this point, because then I will not be able to use their new ray tracing stuff really, and then this rasterization stuff that I talked about I'm really interested in, so I don't want to get a 1080 Ti at this point. It's just like not worth it. but I was thinking maybe I'll get something like really cheap, like I don't know, something really bad. What's like a not awesome card? Is there like a 1040? There's a 1050, so there's like a 1050 for 140. Well, it's a bit of waste. Oh yeah, right, so there's like a 1030 for $85. So maybe I'll get like a 1030 just to get a GPU, and then I'll just wait for 2080 to become available. Alright, anyway, thank you guys for watching the stream. I will publish the stream on YouTube. I will link it on Twitter. We did get the thing working, so this was great. I don't know if it'll end up being inside meshoptimizer, because I'll have to think about whether it's good enough to be practical and what things from the prototype I need to fix and how long it'll take. Alright, thank you guys. Bye. We will end the stream.